Introducing PDCCH channel, physical downlink control channel. We learned that it is kind of can convey the downlink control information, or we call it as the DCI. And we have discussed one thing, that is what is the kind of format that PDCCH can take. So we have studied that. So we understood that PDCCH data is typically represented in terms of something called as CCEs, or uh, control channel elements, which we name them as. And there is some particular rules for this CCE. So CCE would be taking 6 resource element groups. A resource element group is indeed 72 resource element size in total. Again, a resource element group is typically defined as, you know, uh, one resource block by one symbol. Now, to send the PDCCH data, how many CCEs are required? That is dependent on the aggregation level. This aggregation level indeed would be decided in the live situation, depending on, you know, um, what is the present CQI values that are being reported from the mobile. If mobile is in bad radio conditions, so you try to use a higher aggregation level and use a very higher coding, higher level of coding, so that PDCCH decoding would be successful. So that time you increase this aggregation level. So obviously, if you are mapping of aggregation level to the number of CCs is like 1-to-1 almost. If you require aggregation level 2, the number of CCs you need would be 2 to carry the DCA information of a subscriber. So obviously, you require to reserve 2 CCs of this particular size. Okay, we learned this. Now, where does this, how does this PDCCH resource blocking would be done in 5GNR, and how allocation works out for different CCs for different subscribers? So we are more or less interested in that right now. Whatever the data that the PDCCH conveys, that information, where it will come, it should be decided on the live situation. So subscriber, how many subscribers are active, how many subscribers the Gnode B is sending the scheduling information, and what is the aggregation level for each subscriber, etc. But first of all, they need to reserve some resources, uh, for the purpose of this activity, like kind of in a semi-static way, or at least in a fixed way. So such a mechanism is what we call as core sets, which represents that control resource set, the resources that are available for sending control information, nothing but your PDCCH resources or PDCCH data. So how the name came is from this particular, way of extracting the letters from it. Okay, so core set, control resource set. What is it? It is a set of frequency or time domain resources where PDCCH can have CC is placed to transmit the downlink control information. Both in frequency domain as well as in time domain, it must be representing. So it consists of n number of RBs which belongs to this core set in the frequency domain, and it is also going to consist of n number of symbols in the time domain belongs to core set. And how many resource blocks are reserved for this core set operation in frequency domain? How many resources are reserved for its operation in time domain? That is going to be dependent on one higher layer parameter called as control resource set that mobile equipment would be getting, yes, either during system information, or it is, if it is we are talking about a dedicated situation, the information would be provided by RRC, radio resource control protocol, at higher layer level, especially when the mobile equipment is connected to Gnode B, communicating with Gnode B consistently. At that time, this information would be provided. But mostly information would be provided during the initial phases itself, like system information related time. Okay. Now, frequency domain resources and the information related to it. Core set occupies the subcarriers in multiples of 6 resource blocks. And the core set should not cross your bandwidth part. So it is like restricted within the bandwidth part. Now, the number of resource blocks that are reserved are given by this frequency domain resource parameter, that is a subparameter that is present in this control resource set. Now, this frequency domain resources that are allocated, the size of it to be 45 bits, and it works on some concept called as a bitmap, where every bit represents a group of 6 RBs starting from the, your bandwidth part starting position, uh, whether that particular 6 resource blocks have been allocated for your core set or not. So totally, it can represent almost up to 45 into 6. It's like 270 resource blocks. It can identify whether that are allocated for core set or not in the time domain. Oh, sorry, in the frequency domain. So that's the maximum. But core set not only would be occupying frequency domain resources, but it would also be occupying time domain resources as well. Maximum 3 symbols can be occupied by core set in a slot. So that is represented by n sim core set. And again, it is given by a higher layer parameter called as duration in the RRC messages. But this n sim core set is equal to 3 is possible only if the DMRS that is present on the PD's SCH channel, if its position gets shifted to 3. If the position is 3 means symbol number is 4. Only if the DMRS gets shifted to symbol number 4, then you can have these PDCCH occupying the 3 symbols, because otherwise they would be overlapping. You can use it only, you can use the symbol only for one purpose, either for PDCCH core set reservation purpose or for DMRS purpose. You can't do it for both. So this uh, 3 number of time domain resources that are reserved for core set could be 3 only in this particular condition. Okay. So the total resource element groups, REGs, that are present in a core set It is represented with this technical word called as REGs, resource element groups. What is it? I'll introduce. So number of REGs in a core set is a multiplication of number of resource blocks present in the core set in the frequency domain into number of symbols that are present in the time domain. That gives you REG, resource element groups. So how this information, PDCCH resource element mapping information would lead us into an example. Now, if you see the left-hand side, it is representing a big bandwidth part of size around 270 resource blocks, but divided into 45 units. Please, you have to understand, in each and every block here, there are 6 resource blocks present. So total number of resource blocks are 270, which is because there are 45 such cells, 0 to 44. So each one, you indirectly, you have to imagine that inside that there are 6 resource blocks. But why have I taken only 45 here, 0 to 44, 45 units? Because whatever the frequency domain resources that are reserved for this core set would be represented as a six resource block, group with 1 bit. So there are only 45 bits to represent 45 groups. Okay. So that is the frequency domain part. In the time domain, the maximum number of configurable time domain resources are going to be 3. Maximum, that is. That too with the condition I have explained you. Okay, now let us assume that the frequency domain resources, the particular parameter that whatever we have got, that parameter 45 bits indicated these values. In that, for example, we are considering some 12 bits are set to ones, remaining all the bits were set to zeros. It is a bit map. One bit would map to one unit. So now the meaning it conveys to us is that we have our GNODB has reserved 12 into 6, 72 resource blocks to send PDCCHs are reserved for core set. Of course, inside it you have to make PDCCH sit. Or the DCA information set. Now the duration is 1 in time domain, so it is simply occupying only that much, only in the frequency domain. Typically, these PDCCH channel would be present once in every slot. That means you can do the reservation once in every slot for the resources that are present in that particular slot. Okay. Now, as you can see here, if more number of bits are set to ones, that indicates more number of frequency domain resources. How many number there are? Maybe 12 plus 12, 24. Like you have 24 into 6. That many resource blocks are reserved for carrying core sets. Now, it need not be contiguous. It could be disjointed, just like this. For example, you could reserve some, sets of resource blocks over here and leave something in the middle for maybe PDSCH operation. If you don't reserve anything, if you don't reserve these things for PDCCH, definitely they are available for PDSCH consumption. You can send, you can schedule and send the traffic on it for some particular subscriber. Usually won't be done, even though this particular choice is given only in very critical situations, they might be configuring the things like this, when some here, some here. But which is allowed, obviously. But now, with these three examples we have studied in the frequency domain resources, now you can apply that for multiple different durations. So if you consider it for duration 2 in this first example, so whatever the number of resource blocks we have reserved in the frequency domain into 2 in time domain now, even those symbols are also reserved for your core set to carry the downlink control information. Same thing is applicable here for this example. If duration is 2, the same thing is replicated. Here also duration is 2, the same thing is replicated. Duration is 3, it would be replicated another 2 times instead of 1 time. Okay. Now we are going to do further analysis of this. For that, we take maybe this one, 3 unit 1, duration 3, and the frequency domain resources we have reserved are like 12 blocks is equal to 12 into 6, 72 resource blocks. 72 resource blocks into 3 symbols in time domain. We're taking it for further analysis. Now, the REGs are resource element groups. How many are available in a core set are actually numbered in increasing order of time domain first manner normally. But the number of REGs is the formula n in uh, number of resource blocks in core set into number of symbols in the core set. So if you expand it, it would look like this. For example, if I'm expanding this part to see how many REGs are located in it. So you start with REG 0 and you go up to REG 35. Now remember, REG is what? 12, uh, 12 symbols are in 12 different subcarriers, which is equal to 1 resource block size. But this part is not representing 1 resource block. This is 6 resource blocks. This is 6 resource blocks. 6, 6, 6, 6. Now in each resource block, you will have a lot of symbols, a lot of resource blocks in each and every block here. So 6 resource blocks here. Each resource block I'm representing with REG 0. But if you see the numbering, you must increment the numbers in the time domain first manner. So first we have to go on to the right, then we again go up in the frequency. So REG 0, 1, 2, 3, 4, 5, 6, 7, like this. We number them all the way up to 35. This is only taking this part. So how many resource element groups we have are 35 here. But if you have to take how many resource element groups we'd have in the total bandwidth available for core set, that would turn out to be 215, 216 total. It starts from REG 0 up to REG 215. If you take the whole block, it's a simple calculation in how many number of elements present, you're into 6. So definitely the number of elements here are 36 because this each line is 12, 12, 12, 12, 36. 36 into 6. In each one, we have 6 resource blocks. So each resource block is equal to 1 REG. Now, for the purpose of communicating the details to the subscriber, these REGs would be further bundled. So we'll kind of group these REGs that are available into bundles. Again, when it comes to this bundling, there are two ways we can bundle them, with REG bundle size being 6 in case of non-interleaved CC to REG mapping. Now again, what is the meaning of interleaving? Interleaving is whatever the CCs that are, whatever the REGs that are available for you are not contiguous. So maybe one REG here, one REG here, one REG here can be allocated to you, but not that discrete. But I'm telling you, like, so it will be frequency shifted. So in different frequency positions, you will find out different pieces. So the idea is to improve, uh, mobile equipment's chances of successfully decoding PDCCH. Reason is if you try to put them all together at one place, and if that particular frequency is affected for the subscriber while receiving because of the interference or other issues in the network, so the entire receiving thing would be failed, because if you cannot decode PDCCH, you can't download PDSCH, because you don't know which resources are allocated for you as the information is conveyed here. All right. So they'll be bundled in non-interleaved technique. It is bundle size is 6. So if we have 2 and 6 REGs, they would be bundled into 2 and 6 by 6, 36. They would become. But in case of sorry, this is not non-interleaved. This is interleaved. In interleaved case, we are going to have 2, 3, or 6 bundle size. So these REG bundle contains REGs which are numbered from IL. If you take L value as 6, I starts with 0 at the starting, bundle number 0, 0 into 6, 0 into 6 plus 1, like that, 0 into 6 plus 6 minus 1, which is 5. So totally what we'll have is 0, 1, 2, 3, 4, 5. So the first 6 REGs will be put together. We call it as REG bundle 0. So if we do the splitting, total we have 216 REGs are there. They are now bundled into 36 bundles, numbering from REG bundle 0 to REG bundle 35. Because always we start with 0. Now, each REG bundle can carry one CCE, if you can now do the calculation. Because REG bundle, we are taking, please remember, we are taking non-interleaved case. In non-interleaved case, bundle size is 6. So every bundle is equal to 6 REGs. In fact, in PDCCA channel, when we have studied, your CCE would be carried on 6 resource element groups. So obviously, so if you have 36 bundles, you can carry 36 CCEs. It would be straightforward if you take the case of non-interleaved scenario. But for interleaving, for non-interleaving, the numbers would be the same. 0, 1 to up to 35, they would be the same. But for interleaved case, this is opposite. I think my copy pasting mistakes. So this is the non-interleaved case. This is the interleaved case. So in interleaved case, you have to apply some amount of shifting and interleaving. So by substituting some known the element values, you will be able to find out how much amount of interleaving happening. That means that these bundles are not going to be numbered like this. They'll have some amount of shifting. For example, if a user who is using aggregation level 4 require 4 CCEs. Those 4 CCEs would be allocated in 4 different frequency locations. So obviously what happens, even if one bundle is completely corrupted, you have at least other 3 bundles received. From that, you will try to extract the information. Because when you are using aggregation level 4, whatever the DCA data you have, you are replicating it 4 times by using heavy amount of coding, creating metadata and extra copies in order to make your PDCCH reception successful. So you're going to distribute that throughout the band. So how to do that interleaving concept? All these terms you take and you substitute, you'll be able to find out like which uh, which REG elements would be present, which bundles will be numbered as which CCs. You would be able to find out from these equations, which we don't go into. Now, there can be many core sets in a carrier identified by using higher layer parameter called as control resource set ID. And this control resource set ID must be unique across all the BWPs. So if operator required, operator can configure multiple control resource sets in an operating cell. Now this control resource set ID, when it is set to 0, it represents a special control resource set called as control resource set 0, which is going to convey information about set space 0, like where exactly your SIB1 related scheduling information you can find. It conveys the information about that. Control resource set 0. This is configured in MIB. We already have seen that in our previous session, how this control resource set is carrying the data. Now, other core sets are configured by SIB1 or dedicated signaling at RRC. And the maximum number of core sets that can be configured is dependent on the 3GPP release. In release 15, you can configure up to 12 numbered from 0 to 11. In release 16, you could configure up to 16, 0 to 15. So obviously, PDCCHs would be transmitted on these core sets. But which PDCCH that a UE should receive, where that PDCCH is located, is going to be further dependent on something called as set spaces. These set spaces are simply a division of the core sets in a logical way and marking them. Marking them on the basis of aggregation levels so that it would become easy for the mobile equipment to detect, exactly its PDCCH is going to arrive at which location. So what are the different set spaces you have? Set spaces are divided into two major categories: CSS, USS, common set space and UE specific set space. First of all, what is this set space? It is an area where mobile must monitor the elements of the core set to detect its own PDCCH data or the DCA information in it. Now, which set space the UE must monitor is defined by RNTA type. Mobile would be using different radio network temporary identifiers in different situations. Depending on what RNTA it is operating on right now, or what configuration has told you, RRC configuration has told you, you have to be listening to that corresponding set space area. So if you take these set spaces, common and UE specific, in common we have again, uh, 5 different types of, we can say, subset spaces defined as type 0 PDCCH, type 0A, type 1, type 2, type 3, etc. Now, for each set space uh, is applicable for what RNTA types that are listed over here, as you can see. So there are different types of RNTAs. Each RNTA would be used for a specific purpose, a particular purpose. And here on the right hand side, far right hand side, what information you would be receiving, or what information related scheduling would come to you in this particular set space in this location. For example, SIB1 scheduling information you will get to know if you read PDCCH, type 0 PDCCH, which you typically either receive in SIB, or it is configured in the form of set space SIB1 or set space 0 in PDCCH config common as part of the system information blocks. Either it arrives in MIB or it comes in SIB. But why SIB1 related scheduling information can be found out in, you know, uh, PDCCH config common, which you receive in SIB1 again. Actually, this PDCCH config common you receive in SIBs, system information blocks. Then how can you receive SIB1 scheduling details in this config common? It is not about the same cell. If you wanted to know the configuration, SIB1 scheduling related details of the present cell that you are operating, you must receive it in MIB. So that then definitely it would be present in MIB. But typically this PDCCH config common that is coming up later, a later point in time, may be required for you to get to know about the SIB1 scheduling and the adjacent cell that you may be going into as part of your handover procedures or something like that, which we'll anyway see later. But it is used for the adjacent cell purposes. Now, if the mobile would like to know where its system information is going to come, other system informations, the total system information that gets broadcasted in a telecom network is divided into multiple different parts. The system information, the main part is called as MIB. The MIB would arrive in PBCH channel, which we have already studied. Then you are going to have SIBs, system information blocks. Again, in them, you have one thing called as SIB1, which is crucial one. And then you have other SIBs, like you will start from SIB2, system information block 2, almost up to system information block 19. Different blocks of data. And each block of data is required for the mobile equipment to, for different technical reasons, to do different things in this particular cell. It will convey. So if you would like to know where the other SIBs, SIB2 to SIB1, SIB19 are scheduled, you must be looking at the set space, other system information set space part, wherever it is located. There you have to look for to find out the scheduling information. We learn about something called as random access procedure. Related to that random access procedure, when mobile is operating on this ARIA RNTA or temporary CRNTA, then this ARIA set space is applicable for the subscriber. Similarly, paging set space is to get the incoming calls, works on PRNTA or paging RNTI. Anyway, we'll introduce all these RNTAs at a later point in time. What is the purpose of each RNTA? So this is to find out where your incoming call related advertisements are going to happen, where you have to download your paging related data, how where it is scheduled. That scheduling information would arrive on this paging set space. Now, there are a lot of other set space type is set to common, which is arriving on the PDCCH config, but it is not PDCCH config common, but PDCCH. It is applicable for all the RNTIs related DCA formats. What is the DCA format also we'll study. Uh, but it is used for power control, etc., which also we will be looking into. Now, the other segregation is UE specific, where only UE specific scheduling would arrive in this particular location, wherever it is, PDCCH config, UE specific related set space type. So either you will find out your PDSCH related scheduling information or PUSCH related scheduling information in UE specific set space. But how these set spaces are configured? So it's clearly told like this about the set spaces. First, there is a set space ID. Even before this, I think I would better. Okay. So there is a set space ID, control resource set ID. Control resource set is nothing but core set. Every core set has got ID. So this set space information you are going to get in which control resource set. And when are you going to monitor this particular set space? What is the monitoring time interval? Here, SL1 typically represents slot 1, SL2 represents 2 slots. Up to you have SL2560, 2560 slots. If you take a slot size is 0.5 milliseconds, in case, for example, if you take 30 kilohertz subcarrier spacing, so 2560 slots is almost equal to 1280 milliseconds, which is 1.2 seconds. Now you will be given two details here. Starting from what slot number, how many slots it will be repeated for you. Two things that will be provided in this particular field, exactly in this location. How to understand this particular parameter, or how mobile understands it. For example, if the monitoring slot periodicity, if it is, let us suppose that it is set to this, uh, SL8 is equal to 4. It is, the value is set like this. The SL8 will tell you that it is going to be repeated every 8 slots once. The 4 will tell you the starting number, the starting slot number in your frame. So you start with the slot number 4 and repeat that every 8 slots. So if you take the number of slots that are available are, for example, if you take 30 kilohertz subcarrier spacing, you will have 20 slots. So you'll have 4 plus 8, 12. That's it. In that radio frame, you will not have anything in anything else. So in slot number 4 and in slot number 12, there will be this particular set space available, and you have to look for in that particular set space. And there can be multiple set spaces configured. Each set space has got this kind of an ID. And what are the monitoring symbols within the slot? That talks about the time domain within the slot, where you have to look at. And how many number of aggregation level 1 candidates available in that set space, how many aggregation level 2 candidates, 4 candidates, 8 candidates, 16 candidates. For example, one candidate is set to 4. If two candidate it is set to 2, maybe 4 and 8 candidates are set to 1 1. Maybe aggregation level 16 candidate is set to 0. That kind of tells you totally how many CCs are needed. So here you require to, for this particular set space, you need totally 4 CCs for aggregation level 1 and 4 CCs for aggregation level 2 and 4 CCs for aggregation level 4 because even one it will require 4 CCs. In here for 8 you require 8 CCs in total, so you require 20 CCs for this particular set space. That's how it is that. So the number would tell you like totally in this set space how many CCs which of which size you have. Now again, this set space, whatever the available candidates, your aggregation level candidates that are available in total, they would again get divided among this common and the UE specific part, which I did not put it here. I'm expanding that in the next slide. Now, if you take a look at it, this is the set space type applicable for common. Like if you choose DCA format 2.0, again in that how many aggregation level units are there and so on. If it is UE specific, again UE specific related information would be present. That would be explained. What is this DCA formats? We'll understand this DCA format parts. For this UE specific, which DCA formats are kind of applicable for you. Typically 0010 is for 00 is used for uplink scheduling, PUSCH scheduling. 10 is used for downlink scheduling. 01 and 11 also for uplink and downlink as well. Okay, but different types. All right. These are set space extensions which are newly added up in release 16 for new DCA formats. This is for DCA format 2.4, DCA format 2.5, DCA format 2.6 is not added, nothing much now. DCA format 2.7 and so on. So with every passing release, they are implementing new DCIs. So again, set space extension release 17. So there are new monitoring sizes that are identified. So now it is slot 132 up to slot 20,480 slots. Once also you can monitor. So they have increased those number with the next releases. And there are now some more common uh, formats have been introduced, DCA formats and so on. Release 17. Okay. First of all, what is this DCA formats and why are we referring to that again and again? DCA format is simply a logical number that is identified to tell you what kind of scheduling information you are receiving. For example, as you can see the total categories here in the DCA formats, There is category 0, which is subdivided, category 1, category 2, and category 3. Each category is kind of you got it for. Whereas DCA format 1 is conveying the scheduling information for downlink. Now again, DCA format 2 is used for general purposes. Like for example, one thing that we can easily identify here uh, is this TPC commands, transmit power commands, to do the uplink power control. What is it? Will study again this uplink power control. So most of them are for you know uh, general purposes, which are not like telling you which resources are scheduled. If you remember the kind of concept that I have explained you, we have the physical layer in the mobile and we have the physical layer in the Gnode B. We are taking these two components in place. So we have this control block in both physical layers. We have the control block in UE as well as Gnode B. If you receive the DCA formats 0 or 1 from Gnode B to UE, for example, if DCA format 0 is received, mobile understands that 0 anything underscore, it can be anything XYZ, doesn't matter. But whatever is received, UE understands that, oh, I have been reserved with uh, PUSCH scheduling. Now, by reading that information, I will get to know which PUSCH resources I could use uh, for transmitting something in uplink direction. When UE will have to transmit something in uplink direction, especially on PUSCH, UE is a physical layer. Right now, which one we are seeing is physical. We'll have to get a transport block from the MAC layer. And the transport block gets converted into signals and it would be transmitted on the PUSCH, physical uplink shared channel. So it has got this DCA information is downlink control information. It would come here and it would be understood by the control. But once the control understands, it understands that we've been allocated with the uplink resources. So we convey this to MAC layer. MAC will prepare the transport block and give it to us. We process it, send it on the PUSCH channel, physical uplink shared channel, which is just like a downlink shared channel that we have studied. Physical downlink, it is opposite physical uplink. All right. Now, if it is the uh, DCA format one instead of 0 something, if it is 1 underscore X, then it is kind of communicating to you information about which downlink resources are allocated for you. So what is that? If 1x is received from the Gnode B to the mobile, mobile understands that I've been allocated with so and so PDSCH. I have to download the PDSCH, which is going to come to me next in downlink. In some particular identified time, it is going to come to me. I will download that PDSCH and I will process it in the physical layer. And after processing, I would extract a transport block and deliver the transport block to MAC layer. So one is talking about uplink resources, one is for downlink resources. But now the third one, this second section, any information that is coming on the second section is clearly information from this control to control. For example, if you receive these TPC commands, transmit power commands, how much power you have to kind of use for your uplink channels, it kind of conveys that. That means while transmitting your uplink channel, like PUSCH channel, how much power you have to apply, how much power you have to use for it. It will convey that. And that information is not telling you that there is a there is a code word arriving and please download it, or there is some amount of data arriving on an PDSCH channel, download it, or please send some data on PUSCH. It is not telling you to download any data when you are receiving these two formats. You understand that this is general information that is arriving from the GNODB's physical layer control to UE's physical layer control, notifying various different things, which we will be introducing, at different locations in our future sessions. Now, what about this format, the format 3? These are used for NR side link, for example, V2X kind of scenarios, vehicle to everything kind of scenarios. This is for LTE side link, using the side link or V2X on LTE network, or you're dealing with an LTE on the side link as a side link device that time. Now there is some multicasting related traffic, multicasting and broadcasting related traffic where TV is getting broadcasted, or some things are like that. Like when you are sending information to many people, which will be called as multicasting, or send it to everybody, it is called as broadcasting. So if you are doing any of those multicasting broadcasting aspects, then we will be using series 4. So this series 3 is for V2X and side link related things. Meaning of side link is one mobile or one UE communicating with the other UE directly. This is called a side link. Uh, we get to see it a lot of times, but we'll ignore most of the time. We are not studying anything related to side link. We have GNODB and UE. GNODB to UE, we call it as downlink. UE to GNODB, we call it as uplink. But if one UE is communicating with the other UE, we call it as side link. So this is to achieve the V2X kind of things, like vehicle to everything, to do this, to create the self-driving cars and so on. So those are the categories that we have. Now we will have a look at, because we have studied about downlink already, downlink channels and downlink PDSCH channel especially. So we can actually study uh, the downlink related DCI information that is being received in the form of CCE in the set spaces that are configured for the subscriber, where you are receiving downlink scheduling information. So this is DCI format 10. Contains a lot of details. Let us look into these details one by one. First, identifier for DCI formats, the first one. It is 1 bit. It is going to be set to 1, representing that it is downlink DCI format. Conveying to the mobile whatever the scheduling information I'm providing you is for downlink. Next, you have variable number of bits that are going to convey which frequency domain resources are allocated for your operational purposes. That means that the PDSCH that is going to come to you would be occupying how many resources in the frequency domain in terms of resource blocks. Stop. In terms of uh, resource blocks, but the number of bits are conveyed to be variable, and the variable factor is dependent on this logarithmic equation. The number of resource blocks that are available on your bandwidth part, if they are increasing, the number of bits that are required to convey this frequency domain information also would increase, because you need to be conveyed about which resource blocks are getting allocated for you. So there is a formula again called, normally there is a number provided to the subscriber, which we call it as RIV, resource index value. From the resource index value, mobile would be able to derive how many resource blocks are allocated for its operation, and how many contiguous resource blocks are allocated. Those things it can derive. But to send that RIV value, how many bits are needed, that would be dependent on this logarithmic equation. That is going to be dependent on, again, the number of total resource blocks that are available in your bandwidth part. If there are more bits, you will have to reserve more bits to convey this information, frequency domain resource assignment. Time domain resource assignment is going to be conveyed by 4 bits, which will tell you how many time domain symbols are allocated for you in your slot. The possible number that you can go up to is, starting with 1, you can go up to 14. So 4 bits are enough for conveying that information, because 4 bits can convey the value up to almost 15. uh, because the 4 bits, the maximum value possible is 111115. So it kind of conveys that details, time domain resource assignment. Now, whether VRB to PRB mapping is there or not there, interleaved or non-interleaved. Interleaved, non-interleaved situation is the same. Whatever the resource blocks that are allocated for you, or for your downlink operation, are they getting allocated contiguously, or one here, one there? If you are getting one here, one there, so that is to provide you, some security from frequency hopping related issues. For example, if you provide all the resources for the subscriber contiguously in one particular frequency location itself, if the, as I told you earlier, if the frequency location is impacted by the interference, you will not be able to download anything. Instead, they wanted to kind of do distribution into different places. In that case, this VRB to PRB mapping comes into the play. So this bit will represent whether VRB to PRB mapping is present or not present. So 0 means it is non-interleaved allocation, it is straightforward. 1 means it is interleaved. That means the VRB to PRB mapping must be calculated. There again tables for that. So where to look, how do you calculate which location or which resource for you. The next 5 bits are modulation and coding scheme. If you remember, uh, I have explained to you about this channel PDSCH activity, and told you that PDSCH uses something called as adaptive modulation. It uses adaptive modulation and coding. In shortcut, we call it as AMC. So this is the technique that they normally use. On what basis? On your channel conditions. Now, if your channel conditions are getting deteriorated, CQA value is going down, mobile is finding that the channel quality is going down. So obviously, it will report the CQA value to Gnode B. Gnode would be on the live situation, it would be changing your modulation scheme. If you are using higher modulation earlier, it would be reduced. Or if you reported that your CQA is becoming better and it is becoming good and excellent, when you report that, typically your modulation scheme would be changed again as well. Your modulation scheme would be upgraded. If you are using QPSK, you will be upgraded to 16 gram or 64 gram or 256 gram, depending on what kind of a CQA value that you have reported. Coding also would be adjusted almost along with the coding rate. Coding rate can be very high in bad channel conditions. Coding rate would be low in good channel conditions. Because coding is required for what purpose? Error corrections. If CRC is indicating you that there is a error, to correct that, we require this coding part. Okay, now what is this 5 bits and what will it represent? If you have any field as 5 bits, the maximum value that is possible is 2 power 0 to 2 power 5 minus 1, which is 0 to 31. These are the values that are possible for 5 bits. So those 5 bits, mm, I will stop using this. So those 5 bits would represent the values from this particular table, this MCS index table. Either this first table is applicable for the subscriber or the second table, depending on whether 256 QAM gets enabled for the subscriber or not, or if 256 QAM is configured in the cell for the cell operations or not. For example, if 256 QAM is not applicable for the subscriber, then the first table is applicable, where depending on the MCS value that you get, 0 to 31, depending on the value, your modulation order would be identified. So mobile recognizes that, okay, in so-and-so resources, my data is incoming, so-and-so resource elements. But when I have to demodulate those resource element symbols, uh, I have to find out which type of symbols are located. Are GNODB is sending me the symbols, QPSK symbols are, 16 QAM symbols or 64 QAM or, what are being sent to me. So as you can see here, the modulation order QM, when it is representing 2, that is representing QPSK for you. And if it is 4, it is 16 QAM. And then when it is 6, it is going to be, 64 QAM. You can send 6 bits at a time in a symbol. So GNODB is giving you the hint because this is a downlink, downlink scheduled DCA information that we are studying right now. Now, the higher the MCS value, the better. Even though QPSK, in this particular modulation order, but your coding rate that we consider is different. So as the coding rate, as you can see 2 here, the coding rate is ranging from 120 to 679. Of course, the coding rate goes into some mathematical equation algorithm, whatever the value is. But the higher the value, you can consider that the coding rate is actually getting dropped. Number is increasing, but it will drop the number of coded bits. Your spectral efficiency will increase. That means you would be able to send more data bits, even with the same modulation rate, because you are dropping the coding rate, you're decreasing the coding rate, so you could send more data bits. You can take more data from the transport block and add less coded bits to it as part of your coding operation. The higher the spectral efficiency, the more effective your channel is, the more data rate you get. Obviously, that increases further with even higher modulation. So if you can go to 4, 6, as you can see, the last thing that you get with 6, 28 is 5.5547 spectral efficiency, which typically means on one symbol position, you are able to kind of carry 5.55 bits, or 5 times your data rate is improving, 5.5 times. That is the literal meaning of it. But now, what is the bottom 3 things, 29, 30, and 31? Why the coding rate is not decided, and why the spectral efficiency is not mentioned? These 3 numbers, 29, 30, and 31, would be used only in case of retransmissions, when your data is getting retransmitted. So when you report a negative acknowledgement for the data that you have received in downlink, the GNODB would be retransmitting the things. At the time of retransmission, it would be using the same modulation that it have used earlier, normally to start with. But if your data is again failing, typically it will drop the modulation order. So at first it may tell you the number 31, later can shift to 30 and then 29. So obviously the modulation order is 6, 4 and 2, 64 QAM, 16 QAM, and you have QPSK that are in order. So this is for the retransmission purposes. For example, your transmission happened with number 24. Typically that started with 6 during original transmission. If that is failed, you think that it is failed because of some issue. Maybe later if you retransmit, it would work. You may try out with the MCS index number 31 by using 6 itself. But it again failed. So it might drop. It might still indicate you that it is retransmission, but it might drop the MCS value, which is 31 or 29. So when drop means it's going to send the same transport block once again to you, but by using less modulation. That means by using more resources. Now the table that is present on the right hand side is applicable when 256 QAM is enabled for the device. You can see now the modulation order is 2468. Some of the entries, some of the rows are containing 8. And your spectral efficiency is going all the way up to 7.4063 with the maximum value possible 27. And for again retransmissions, here we require one 8 thing also. So 31 is 8, 30, 29 and 28 respective retransmissions will take up those values. It is a kind of way of giving a hint to the mobile equipment that it is not a original transmission, it's kind of retransmission if these numbers are used. But overall, uh, so this MCS index value will give a hint about what modulation and coding scheme is in place. Next, new data indicator is again a way of straightforward indicating to the mobile whether whatever the data that is scheduled to you, is it new data or is it the old data that is getting retransmitted. If the new data indicator is explaining the mobile equipment that it is not new data, it is old data, that means mobile might have reported negative acknowledgement earlier, and as because of that, it is sending the transport block once more. That's the literal meaning of it. Next, redundancy version, 2 bits. This redundancy version, the possible values are 0, 1 to 3. Each one is going to tell you different redundancy versions of the coded bits. I've told you this concept while introducing the HARC mechanism. I've told you something called as incremental redundancy, where every time when you are retransmitting, you would be using different form of redundant bits to effectively decode the data. Next, HARC process number 4. So what is this HARC process number? So this is a feature that I have not explained you earlier. First of all, what is the meaning of a HARC process? We already know what is the meaning of HARC. HARC is an hybrid automatic repeat request, which is a newly introduced feature that is available in these radio technologies of improving the ways of correcting the data in case of errors by using incremental redundancy and chase combining, etc. And if everything fails, go for the backward error correction. HARC's main duty is to receive the data that's arriving and try to decode it intelligently. For this purpose, ARC definitely requires some amount of memory. Why it is needed to have the memory? Especially on the receiving side, the memory is required. Of course, on the transmitting side also memory is needed, but I will explain each one by one. First, we'll take a look at from the receiver point of view. Why the receiving ARC entity needs some memory? First, it received a transport block. Its CRC tried to verify. CRC failed. You tried to correct the errors with the help of the coded bits. Again, that operation also failed. Now you have to request for the retransmission by sending a negative acknowledgement to GNODB. But because we have this concept called as incremental redundancy and chase combining, as part of it, you have to maintain the previously received transport block and its CRC bits and everything. As a package, you have to maintain it. You cannot throw it into dustbin because you anyway you have asked for the new transmission. No, you should not. Because it is a hybrid feed mechanism. It wanted to use the previously received data plus it wanted to use the new copy also, because there is no guarantee that the new copy also would be successful. There might be failure as well for it. So it needs to store it. So it needs memory. Now, how much time you require this memory till you solve this problem of the transport block until it becomes successful? You might have to do 3 or 4 retransmissions if required. All the while you are doing it, you keep storing all those copies that are arriving to have an effective way of sorting this out. Now, if you consider this ARC process is some kind of a core in your computer, if the idea they created is, if one ARC processor, if one ARC core, if it is busy, already stored some data and waiting for the transport block that is arriving, what about the fresh data that is arriving in the next TTI, next transmission time interval? Because by the time you send the ACK and receive the retransmission, it might take some time. It might, for example, take 4 symbols or 5 symbols. But what about the data that is immediately coming to you? Should you be ready for downloading that? Actually, yes, you should be ready immediately to receive the fresh data. But then what do you do with the data that is already stored? You can't delete it until you complete your retransmissions and reconstruction. So that's why they created the mechanism of creating multiple ARC processes. Like there are like multiple cores. In order to easily understand it, you can take it. In your CPU, you have dual core, octa core, quad core, things like that. 8 cores means there are 8 processing units on your CPU chip, which can do computations like mathematical computations or anything needed. 8 of them can parallelly work so that your functionality that you are trying to achieve on your system would be finished faster. So this ARC process is the same way. ARC process is like that core. So there will be multiple ARC processes. GNODB is kind of controlling this and telling the mobile equipment, hey, to download and process the particular PDSCH transport block I am scheduling to you now, which process number you have to use. Please use this process number. It would convey that number. So it's kind of a coordination effort. So there will be multiple ARC processes. How many here? 16. 0 to 15 are possible with 4 bits. Next, downlink assignment index, 2 bits. We'll ignore this. The downlink assignments index, it's only required for multi-cell scenarios or dual carrier scenarios, which we are not studying as part of this course. So we're ignoring it. TPC command for scheduled PUCCH stands for transmit power command. kind of giving a hint to mobile equipment about uh, PUCCH usage. What is this PUCCH channel anyway, which we'll introduce today? Stands for physical uplink control channel, just like we have a downlink control channel that we are studying right now. It is uplink control channel. Uplink control channel is used for sending ARC acknowledgement or negative acknowledgement. If you receive the data in downlink on PDSCH, you need to convey the information back to Gnode B in uplink, like telling the Gnode B whether you have successfully downloaded and decoded that PDSCH transport block or not. You have to report it. On what channel you report it is this PUCCH. You send this ARC ACK or NAC on PUCCH channel. But while transmitting, how much power you should apply for that PUCCH, that is going to be conveyed to you by using this TPC command, which is 2 bits. It kind of gives the uh, power value relative to the previously used power value, whatever the power value you have used earlier for PUCCH. Relative to that, what is the value that you have to use now? Increase the power or decrease the power, etc. So in uplink, power control would be done in a very critical way. Uh, how much power the mobile equipment should use, Gnode would be controlling it totally. It won't give any like easy permission for any mobile to use excessive power because it would cause interference for others. It's related to that. Anyway, we discussed that TPC separately. PUCCH resource indicator. Which PUCCH resource you are going to use to send your ARC feedback. And the next one also linked to it. After you receiving the PDSCH transport block, immediately after how much time you are going to send the ARC feedback. Here 1, 2, 3, 4, 5, 6, 7, 8 represents symbols. After how many symbols? After receiving the PDSCH completely, you are going to send your feedback information in uplink direction, and that too by using which uplink resources, which uplink PUCCH resources. Remember, this is not PUSCH resources, this PUCCH, only control information. Normal, typically very small amount of resources would be provided to you so that you can just send that acknowledgement that is needed to convey whether you have successfully decoded that transport block or not. Okay. So totally, if you take a look at this, the total amount of information, if you consider that for time being, if you consider the frequency domain resource assignment is like, 10 bits, let us assume for time being. So if you count, that will give us the total number of bits that this DCA format 10 would send to the mobile, conveying the scheduling details. 1 plus 10, 11, 16, 21, 22, 24, 28, 32 plus another 6, 38. 38 bits if this size is 10 bits, if the variable size is 10 bits. But this 38 bits, if you take a look at it, it would have to travel on 1 CCE. But these 38 bits becomes a lot of bits after the coding operation. So that is about our overall downlink related aspects. So which frequency domain resources, which term domain resources you are getting to know once you listen to set space that is indicated to you exactly um, which DCA related set space you have to look for. When it is indicated, you will be looking into that set space. Then you get to know about which resources are allocated by reading and downloading that information. Now we are going to go to uplink. What is the uplink structure that looks like when you have to compare it with the downlink thing that we have discussed? Now there are two radio technologies that we have, FDD and TDD. FDD means frequency division duplex, where you get to use two different frame structures, one for downlink, one for uplink. And in the downlink frame structure, you will have only downlink channels placed in all the slots. There are no uplink channels present in it. But in TDD, time division duplex, uh, only one frame structure would be there because there is a single frequency that the mobile would be using both for transmission operation as well as reception operation for G-Node B. That means mobile and G-Node B are both are using same frequency. That is what is we call as the TDD, time division duplex. Uh, which one would be preferred out of these two, FDD and TDD? On what basis normally it would be done? Now there is, according to the bands, each band in which mode we can use is already there. So depending on the band that you pick up, the corresponding technology we would use. But one other scenario is if we use the FDD, you kind of require two bands that you need to purchase from the government. The entire purchasing bandwidth would be high in FDD. So if you are wanted to operate on total 100 megahertz bandwidth, so you are going to have 100 megahertz for downlink and you going to have 100 megahertz for uplink. And between uplink and downlinks, there is some amount of frequency gap would be there. So that mobile and G-Node B, when they are transmitting and receiving, mobile can transmit in uplink by using uplink frequency band and would be receiving in downlink frequency band at the same time. But what is the advantages and disadvantages of FDD? Advantages, obviously high amount of data rate can be achieved. And if you can purchase the high amount of bandwidth for yourself, that's the advantage. And whatever the data rate that you get in downlink, same way, similar data rate you can get in uplink if the band is equal, especially if it is equal. Need not be equal, it can be different, but if it is equal. But there is a disadvantage is, for example, if not too much uplink traffic is being used by the subscribers, most of the times that would be the case. Your downlink traffic would be high, uplink traffic would be very low. For example, if you are watching a YouTube video, for half an hour, 1 hour, you watch the YouTube video continuously, you would be receiving thousands of IP packets and each one is containing a TCP segment in it. Now, that is in downlink. But what you would be doing in uplink is simply your mobile would be sending only acknowledgements for those TCP segments. So for each TCP segment, one acknowledgement would be generated that typically would be very small data, which is like 20 bytes, packed into IP packet and would be sent back to the would be sent back to the server. But downlink IP packet size would be like 1500 bytes, carrying huge amount of video related data. But in uplink, you have to just send acknowledgements. That's all. Your application is not sending anything in uplink. Your YouTube application is just playing the videos. It is not sending anything in uplink. Every now and then, maybe if you are doing some settings like what quality you want or what subtitles you want, it will send that details. That time it will be using some size. Mostly it will be very pretty less size. So now with the problem with the FDD, you would be wasting typically a lot of bandwidth on TDD and you will not have flexibility. For example, if you want, suddenly you wanted a high amount of uplink resources. No, you can't deal with that. That's not possible. Whatever the bandwidth that you have fit in, you have to use it. But the case with TDD is you have that amount of flexibility. which of course that is shown here in this particular picture. These are the different formats that you can have for TDD operation. Now all these are the symbol numbers in a slot, 0 to 13, and we have 0 to 55 different formats. What are these formats, and what's the meaning of these formats? You can kind of do this kind of a division. For example, here D represents downlink, U represents uplink, F represents flexible. You can either use it for uplink operation or downlink operation, and you can convey it to the devices, whether that particular symbol is being used for uplink or downlink. So you have a lot of flexibility. You can play around. You can give one number to the subscriber, one format to the subscriber, and you can choose the flexible formats also. And later you can, depending on whether the uplink traffic is high or downlink traffic is high, you can kind of roam around. Like, you can switch around from sending downlink traffic to uplink traffic, etc. So that's the advantage of using TDD. You will have more flexibility. Your resource wastage would be typically low when you don't have too much uplink data, and if when you have chosen a format which is having more flexible entities, so then you can convert all those uplink things or flexible things for downlink operation. Uplink will have lesser um resources. So how this division works out, this kind of will be provided to the mobile equipment in the form of configuration, a clear-cut configuration, as you can see. Configuration for the TDD slots by RRC SIB information. Like what is the pattern that is being used, and the pattern will give a lot of details, like uplink and downlink transmission periodicity, how often this particular arrangement would be repeated, number of downlink slots, and in that number of downlink symbols, downlink uplink slots or uplink symbols. So slot wise you can segregate, symbol wise you can segregate. So what are you doing? You can kind of configure that entirely. So all this information can be provided to the mobile in the form of SIB, system information blocks, the general system information that the mobile is downloading. From that, mobile would configure the frame structure and understand when to do a downlink and when to go for uplink by using the same frequency. So when you are doing in downlink, you will be listening to that frequency on your antenna. When you are doing uplink, you will be transmitting it on the antenna, the same frequency on the antenna. Of course, the TD slot can be configured even for dedicated use. Like, for example, in a slot, so particular slot number with some index, the symbols are applicable for all downlink or all uplink, or explicitly some symbols are chosen for so-and-so symbol to so-and-so symbol is chosen for downlink, so-and-so symbol to so-and-so symbol is chosen for uplink. So like that, it can be conveyed to the mobile. So if it is, especially if the mobile is doing, if you are, for example, on a video call, when you are on a video call, you kind of need to use both the things. So you would be downloading, you will be uploading. You will be downloading your friend's video and you will be uploading your own video. So you require both. So maybe then now the network would split in the live situation and it will be reported to the mobile. How are you going to use these things? Which symbols you are going to use for what operation? For PDSCHR, PUSCH, etc. It's completely dynamic. Okay. There's one more small concept that we have to introduce called as supplementary uplink. Uh, we won't be studying anything related to supplementary uplink, but we get this information in the specs a lot related to supplementary uplink. We'll be ignoring all that whenever it comes to supplementary uplink when we are studying any of the protocol messages, as we are not interested to learn that. But because it'll come too many times, it'll irritate us. So at least first we'll introduce the topic so that you'll not find it very hard why are we skipping it. But first of all, what is the meaning of supplementary uplink? Why do we need it? Assume that there is one uh, GNODB transmitting unit and which is covering some particular amount of an area, as you can see it over here. Now, when the devices are nearby in this particular area, perfect downlink and uplink coverage would be working out. So that means you can do the downlink as well as uplink. At the same time, it perfectly works out for you. But if you take a little bigger area, maybe downlink would be perfectly working because GNODB can transmit the signal with very high amount of power as it is transmitting especially the signal for all the users together. Normally, what does the GNODB do? It might take the data of several subscribers and put it into different resource blocks. All of them, it will multiplex and generate one baseband signal. That baseband signal gets converted into carrier wave and gets transmitted. That baseband signal and the carrier wave need to be transmitted in the entire area, in the entire region, to the dead end of your cell. And wherever the subscribers are there, they would be able to receive it. And you have to use good amount of power with which the signal must be able to reach every nook and corner of the cell. So obviously, wherever the subscriber is, as it is using adequate amount of power in downlink, as it is a single transmitting entity, it can use good amount of power, and the signal is definitely reaching out to the subscribers wherever they are. But the problem is uplink in this particular locality. In case of uplink, it is the mobiles who does the transmission. But mobiles may not be able to use the same amount of power that GNODB is using. If they use that, the battery would be drained out very fast, especially in cases when you are using very high amount of, your FR2 cases, even if it is even more with higher bands, it will consume more power. And that too, if you are using cases like FR2 or high bandwidth cases, the signal can, with the power that the GNODB is transmitting, signal can travel some amount of distance, good distance. So downlink is possible. For the mobile equipment's power, the signal won't is not capable enough to travel all the way up to tower in uplink direction, as it is having a lesser power source. So what do you do in these cases, in these problematic situations? You go for this mechanism called as supplementary uplink, where you configure it and you kind of provide this information to the subscriber. Hey, with the power that you are utilizing, you may not be able to transmit very high amount of very high uh, band like FR2 band or high bands, but I think lower bands would be suitable for you. I think you can transmit the lower bands with the lower power. The signal can reach me. So I have configured a supplementary uplink frequency here in this particular cell. And whenever your signal strength goes below a particular level, please shift to supplementary uplink instead of using normal uplink. So there is a separate band configured. Of course, operator definitely have to purchase this separate band, or if they are migrating from the old technologies like um, UTRA or something like that, like LTE, so they can segregate some amount of bandwidth from LTE itself, and they can keep it as the supplementary uplink band for 5G users who wanted to have that flexibility in uplink to deal with less, you know, signal strength or less power usage purposes. So there are certain bands that are identified by 3GPP as supplementary uplink bands. Now, in these supplementary uplink bands, whatever the bands you may have, you may be able to use them for your operation. For example, there are certain bands that I've highlighted here as SUL, as you can see, supplementary uplink, N80 onwards, N80, N81, and so on. N80 is 1710 to 1785 megahertz, supplementary uplink. Now, this works in conjunction with uh, your other band that you're already operating. So it's kind of a mixed procedure. Downlink you would be doing on one band and uplink you would be doing on some other band altogether, especially in those conditions where your signal strength is bad. For example, if I have to tell you the supplementary uplink for your Reliance Jio case, it could be this, the first one. Supplementary uplink band N78 in combination with N80. So you are configuring some bandwidth in 3300 megahertz to 3800 megahertz for uplink and downlink both, whatever the band is. You configure that in TDD mode, uh, time division duplex, where resources would be shared between downlink operation and uplink operation. But now, this is when the signal strength is really good. You would be using this band, operating on this band. But when the signal strength goes bad, you would be using N80, the supplementary band that is available. So LTE band can be vacated. A little amount of LTE band can be vacated, especially when the LTE subscribers are going down and 5G subscribers are going up. You can vacate a little band in LTE, and you can allocate it as the supplementary uplink. So now the combination N78, N80, these details would be provided to the mobile. When to use N80, N78 band for uplink transmission, when to use N80 band for your uplink transmission is clearly conveyed based on the signal strength estimations. Of course, the other case we can ignore, the DC band case, dual carrier band, where mobile is using already using two protocol stacks, UTRA plus LTE as a dual carrier technique, two carriers to increase the data rate. In that case also, we can additionally have the supplementary uplink, but we ignore that. Okay, that is little introduction to uplink. Okay, now we are going to start with the actual mechanism that we have to study related to uplink. So first we are going to start with 5G random access procedure. If you remember, the first thing that we have studied in downlink is something called as a synchronization block, SSB synchronization block. Now, why mobile equipment is downloading synchronization block or is interested in it? What is the purpose for that? To detect itself where it is located. Like it kind of wanted to know. So what is the radio frame number that is going on and what is the subframe number that is going on, or what is the slot it is present under right now, and what is the total frequency band that is available. You wanted to know such kind of information. So if you can access that SSB, you can kind of get to know everything related to it, because in the bits and pieces of information that you are getting in SSB, there will be details related to it. So if you have that information, it is good for you. So you kind of saying that, okay, this is nice. I now know what's going on in downlink. But what about the similar thing that you have to do for uplink? We call it as uplink synchronization. And for performing uplink synchronization, mobile would be using one special channel called as uplink synchronization channel, or we typically name it as random access channel. It would use to achieve that. So you have to sync with uplink mechanism. Okay. So downlink synchronization is single step. GNODB transmits the sync signal, which is nothing but PSS, SSS, etc. Mobile, because they are containing um, special symbols, related information present inside it. So you are easily detecting where those symbols are located, and you are identifying and you are synchronizing. In downlink, the synchronization possibilities are continuous, and you can do it at many places, as this SSB block transmission is typically repetitive. It'll keep getting repeated for some n number of uh, you know subframes once. So even if you miss one, you can wait for the next one, and ultimately you will find where some SSB block. And at the moment you find it, you can complete your synchronization by reading the data that these channels are giving you. But in uplink synchronization, what is the issue? In uplink, mobile may be very near to the cell center. Mobile can be very far away from the cell center. Mobile don't know where exactly it is located in the free geographical location. When it transmitted a signal, the received signal on the GNODB side is perfectly being received, or is it becoming too late or too early? Mobile doesn't know anything at all. So when it comes to uplink synchronization, it is not mobile equipment going to transmit any sync signal. It is not that. And the job is automatically done. No. If you have to make mobile transmit the sync signal to make the GNODB adjusting to your uplink transmission, mobile need to keep on transmitting the sync signal forever, continuously, when it will have to continue in the network. But that's kind of not needed. And if you make the mobile equipment to do that, mobile would lose the battery. You can always easily make GNODB do it. GNODB transmit, prepare one thing called as synchronization signal block, and you can make the GNODB transmit it again and again and again and again, no problem, because GNODB is connected to a fixed power source. But UE need this uplink synchronization with GNODB, and UE and GNODB must be in sync in uplink, in terms of uplink, only when mobile equipment is like kind of wanted to transmit something in uplink. It doesn't want to be in uplink sync continuously 24 by 7. If you have to do that, if you think that you must be in sync 24 by 7, you must transmit the sync signal 24 by 7, because your location would be changing. You would be moving from place to the place to the place. So whenever you change the place, your transmission timing is changing with the GNODB. So in order to adjust again, GNODB requires a fresh sync signal from you. But if mobile maintains that, it would be switched off in 1 hour, 2 hours time. So the idea they created is they decided to make the mobile equipment send the sync signal, whatever it is, only when needed. That means there is a possibility mobile equipment can be out of uplink synchronization for a large amount of time, especially when it is in idle mode, not doing anything. But mobile would be maintaining this uplink sync throughout when it is in connected state. Normally, when it is in connected state and doing something, doing some important activity like transmitting the data, receiving the data, when you are doing some activity, definitely you try to be in sync, in uplink sync, and both in uplink sync and downlink sync. You can be in. But with downlink sync, network mobile doesn't require network's help, as network is already continuously transmitting the sync signal. Mobile can anytime do the sync with downlink. Only problem is uplink, because it's a two-step process. UE transmits the sync signal, which we call it as preamble or a signature. GNODB receives that. GNODB do the estimations, uplink sync estimations, and then on the basis of that, GNODB is going to provide the knowledge to the mobile equipment once again. Come back and tell the mobile what's going on. why exactly whatever the sync signal he transmitted, with that sync signal, what happened, how much delay occurred, and based on it, GNodeB would suggest something to the mobile. Now, this uplink synchronization, uh, that mobile equipment have to achieve is going to be called, in a shortcut, it is called as the timing advance. It is known as this synchronization. So whenever this word uplink sync is used, it is called as the timing advance that the mobile equipment will have to apply. What is this timing advance and how to understand it? For that, we'll look at a picture just to understand this, uh, what is the meaning of timing advance and what is the meaning of this uplink synchronization. So we have a tower, we have a cell, and there are three mobiles located in different distances. And here we are going to study the importance of why do we need this, um, uplink sync, or this something called as timing advance, or why we did need uplink sync. First of all, first we'll see that. So we are going to assume that these three guys, one yellow mobile, one green color mobile, and one aqua color mobile. So three guys are there. These three guys are getting the same frequency time domain resource continuously, one after the other. Let us assume that resource is resource block number 7 and 8 in some time domain location. Okay, so like in one slot the yellow color guy is getting, next slot the green color guy is getting, next slot this aqua color guy is getting, in that order. Yellow guy first, green color guy next, and aqua color guy last. Now, the baseband signal that need to be transmitted onto the carrier wave in the first slot is generated by the yellow color wala. That guy would generate the baseband signal first. But this yellow color one is far away from the cell center, is almost on the cell edge, as you can see. Is here on the cell edge. So now when he transmitted the data exactly in the slot starting, what happens? So I'll kind of magnify this here. So you're transmitting the sync signal exactly at the starting of the slot. This is transmitted. But because there is quite amount of distance between the mobile and tower, so this much amount of delay will be there in the traveling. So the reception will come delayed on the GNodeB. Now, the yellow color guy is transmitting in one slot, his symbol, yellow color symbol, finished. Green color guy is transmitting its symbol in the next, in the same resource, in the next time interval, next slot maybe. Next slot, the third guy. So because they are getting it one after the other. But the problem with reception side is on the GNodeB side, as you can observe, because this is delayed while traveling, as the user is very far away. On the receiving side, it would creep in into, the symbol position of the second guy, because it is delayed. It is not arrived immediately. It is not like it gets transmitted immediately received. It has to travel. You can say, hey, radio signals will travel very fast. Yes, they travel very fast. Their speed is equal to 3 into 10 to the power of 8 meters per second, light speed of light. But even light has to travel. Light from, for example, if it's arriving from sun to earth, it take 8 minutes. So there is traveling time associated with it. It will not be minutes and seconds and etc. Micro and nanoseconds it would take. Whatever that is, I'm drawing that value here. Okay, now what happens? The second guy's transmission also gets delayed by by little less amount of time because this guy is in the middle. This guy is far away. This guy is in middle. This guy is near to the cell center. So this guy's signal delay would be less than this guy. If the, for example, this guy is 3 units, 3x unit of delay. This is 2x units of delay, as you can see. But even if this guy's signal is also delayed, but still, because this guy's delay is more, this guy's signal creeped into this guy's signal, basically impacted there. Those two things. Similarly, the middle guy transmitted the signal, received little delay based on the distance. But take a look at the third guy. Third guy is very nearby. His signal started getting received at G node B almost immediately with a little gap. Maybe only X amount of delay happened. But this guy, it started transmission at 2x delay. His transmission gets finished also at 2x delay, which would again creep in into the third guy's signal position. So obviously, because different mobile phones would be at different locations and the delays are different, obviously that would create issue for you when you are, uh, when you are making them transmit exactly whatever they understood as the slot starting according to downlink understandings. So what does Genome we need to do to resolve this issue? Is there any way available to resolve this issue? Yes. What is it? Genome we have to make them start at the starting to transmit something called as a sync signal, some special signal, and Genome must be in a position to estimate that sync signal delay. How much amount of delay occurred for that sync signal? It kind of must be able to estimate that. And after estimating the delay, convey that information to the mobile. Hey, I am estimating 3x amount of delay from your side, but what I would suggest to you is when you are transmitting your signal, you transmit it 3x early, 3x units early. That means whatever you feel that is the starting of the slot, you should not start your transmission exactly at the starting of the slot. You have to transmit 3x units early, you have to start. So this mechanism is called as a timing advance, or we call it as uplink sync. What happens because of this? When this guy starts 3x units early, the reception will be perfectly in sync with GNODB's reception mechanism, as you can see. Whatever the GNODB slot maintaining time, to that slot maintaining time, this perfectly fit in. As this guy started a transmission little earlier, obviously there is a traveling time, but the reception will be perfect after the traveling time. Now you tell the second guy that, hey, your delay is only 2x units. You need to only advance your signal transmission only by 2x units. There is some kind of a gap also between these first guy and second guy transmissions. Their their transmission, second guy transmission need not to start exactly when the first guy's transmission ended. Not needed. It could be little late. Why? Because the distance between the first guy and the second guy is not same. They are not at same distance from G node B. There are two different distances. So first guy is transmitting 3x advanced doesn't mean second guy also need to transmit 3x advanced. No, 2x advanced is enough for him. This signal, after taking the delay impact, it would be able to reach exactly in the correct, slot reception position. So you tell the third guy to transmit only 1x early. and that will fit into the slot position perfectly. That means, what are we doing here? We are making sure that the reception is in sync. The transmission is not in sync. The transmitting guys need not to exactly start transmitting once the other guy transmission finished. That doesn't work out because they are at different locations. You have to make sure that the receiving in is in sync, and one guy's signal and the other guy's signal is not hitting into each other when they especially got same resource allocated contiguously one after the other. Now there is no creeping in here. Obviously, we are solving this issue. So this mechanism of detecting mobile equipment's uh, delay in signal and it is suggesting him about the correct timing adjustment value is what we consider that as uplink synchronization. And this is very vital for uplink operations, not needed for downlink. Reason, all the mobiles together in downlink would be receiving the signal from only one guy. How much amount of delay occurred to it, we don't care. In downlink, when the G node be transmitted, mobile receives that. G node be transmitted, mobile receives it. G node be transmitted, mobile receives it. Of course, this guy will receive first. This guy will receive next. This guy will receive next. Their reception, their reception timing is different, but there is no problem because there is nobody else who is transmitting something to that user at the same time. There's only one guy who is transmitting. But it is not the case in uplink. Uplink, all these guys together will have to transmit to G node B, and they should not fight each other, and they should not corrupt each other's signal, especially when they are allocated with different resources in time. So you have to make sure that the reception should be in sync so that G node B would be receiving each other's signals cleanly. All these guys signals cleanly. As multiple transmitters are here, one receiver. So the concept is completely altered. One transmitter, multiple receivers in downlink, multiple transmitters and one receiver in uplink. So what is that? So UE transmits a special sync signal. We call it as a preamble or a signature. G node B receives that, estimates the sync signal delay, and then provides the information, estimates to the UE. Then UE finds its sync. Meaning is UE know how advanced it need to transmit in uplink. So this uplink synchronization cannot be continuous, as I told you, to avoid the power wastage. It should be done only when it is required. And this uplink synchronization is done by using something called as a random access procedure, which is quite complex. This random access procedure that mobile performs to achieve the uplink synchronization can also be used for various purposes, various other scenarios as well. It can be done. And one of the thing it can be used for is to achieve uplink resources, especially. For example, if you wanted to transmit some information to the G node B, you wanted to request something from the G node B, you wanted to say, hey, G node B, I want to send some message to you. Can you please allocate me some uplink resources? I don't have any. Now you can kind of send that information also in this, you know, in this random access procedure or random access channel. Now you can ask, hey, why can't you send that information on the uplink shared channel, PUSCH? You are allowed to use PUSCH only once it is allocated for you. You just switch it on. You never spoke to G node B and it is never allocated to you. Now, how can you suddenly decide to use the PUSCH? If you suddenly decide to use PUSCH for yourself without it being allocated for you, uplink shared channel, there will be collision with others related data because the PUSCH is allocated for others in the position that you are using. You are not allowed to use that on your own. So then how this mechanism works, how this random access procedure works? For this random access procedure, there would be a special channel used called as PRACH, physical random access channel. which is kind of a common channel, and these common channel resources are conveyed to the mobile equipment in the system information block when mobile is doing the downlink synchronization, when it is reading the system information blocks. So which resources are reserved for PRACH? It is conveyed to the mobile. And mobile is allowed to use these PRACH resources whenever you want to send this uplink synchronization signal called as preamble. Mobile is allowed to use this preamble to, use this PRACH resources to transmit this sync signal or preamble signal to request for the resources. But what if two mobiles decided to use this uh, PRACH channel at the same time? Because the PRACH resources are advertised, and all the mobiles, they have got this PRACH resource related information advertised, so they know when to use these PRACH resources. In your uplink, slot positions, in which uplink slot positions where you can transmit. So you kind of know that, but that information is common. GNODB provides the same information to every subscriber. Now every subscriber know which resources are reserved for this PRACH operation, for sending this special sync signal. So how that works out? Now the problem is when multiple guys are transmitting this special sync signal, definitely there is a possibility of a collision, because all the mobile phones, without coordinating with each other, transmitting this sync signal, definitely there is possibility for collision. But in what cases collisions will occur? What is the meaning of collision? What happens in this collision? How to resolve this collision? How this physical random access channel works, how this random access procedure works is what we have to study. We take a break of 10 minutes, we come back, and then we will see this random access mechanism. 11:45 days.